A few days ago, I worked on this LeetCode problem. You need to create a function that accepts two arguments, n and m, calculate num1, the sum of all integers from 1 to n that are not divisible by m, and calculate num2, the sum of all integers from 1 to n that are divisible by m. The function returns the difference between the non-divisible and divisible sums. This problem is marked as easy, and the naive solution is straightforward. We initialize two variables to 0 for the divisible and non-divisible sums, then iterate over every number from 1 to n inclusive. If a number is divisible by m, we add it to the divisible sum. Otherwise, we add it to the non-divisible sum. Finally, we return the difference between these two sums. This approach runs in linear time complexity O of n, as we iterate through every number from 1 to n. However, this problem can be solved in constant time O of 1 using mathematics. We can define a constant number of arithmetic operations that solve the problem for any arbitrarily large n. This optimized approach will be explored in this video. Imagine representing each number from 1 to 10 as a column of squares, forming a triangular arrangement. The total number of squares represents the sum of all integers from 1 to 10. Now, let's create a visual proof. If we duplicate this triangle, rotate it 180 degrees, and place it adjacent to the original, we form a perfect rectangle. The area of a rectangle is easily calculated by multiplying its width and height. Since we duplicated our original triangle to create this rectangle, the rectangle's area is exactly twice the sum we're looking for. Therefore, we simply divide the rectangle's area by 2 to find the sum of numbers from 1 to 10. Now we'll explore the problem using a slightly different approach. Let's say we want to sum the numbers from 1 to 5. We can visualize this by duplicating the list and reversing it. When we add these two lists, column by column, 1 plus 5 equals 6, 2 plus 4 equals 6, 3 plus 3 equals 6, 4 plus 2 equals 6, and 5 plus 1 equals 6. Each pair sums to the same value, 6. Since we have 5 pairs, each summing to 6, the total of all pairs is 5 times 6 equals 30. However, this total represents the sum of both lists combined. To get the sum of just the original list, we divide by 2, giving us 15. This process reveals the underlying formula for the sum of numbers from 1 to n times n plus 1 divided by 2, which we'll use in our solution. Now we'll explore an example, finding the sum of numbers from 1 to 13 that are divisible by 3. There are 4 such numbers, 3, 6, 9, and 12. We can find how many multiples of 3 exist in this range by calculating floor 13 divided by 3 equals 4. The floor function gives us the integer part, ignoring any decimal remainder. This result, 4, represents the count of numbers divisible by 3 from 1 to 13. Intuitively, if 13 contains 3 4 times, then the multiples 3 times 1, 3 times 2, 3 times 3, and 3 times 4 will all be less than or equal to 13. To find their sum, we notice 3 is a common factor. Factoring it out gives us 3 times 1 plus 2 plus 3 plus 4. The expression in parentheses is the sum of natural numbers from 1 to 4. We can use the formula we established earlier. N times n plus 1 divided by 2. Plugging in 4 gives us 4 times 5 divided by 2 equals 10. Thus, the total sum is 3 times 10 equals 30. This reveals the underlying formula for finding the sum for any values of n and m. Now let's find the sum of numbers, not divisible by 3. These are the numbers highlighted in red. As you can see, we can obtain their sum by simply subtracting the divisible sum from the total sum. The total sum, 1 through 13, is 91, and the sum of divisible numbers is 30, giving us 91 minus 30 equals 61. Using the formulas we've derived, we can now assemble our optimized function. First, we calculate the total sum from 1 to n, using n times n plus 1 divided by 2, Next, we compute the divisible count k equals floor of n divided by m. Then, we calculate the divisible sum using m times k plus 1 divided by 2. The non-divisible sum is simply total sum minus divisible sum. Finally, we return the difference. Non-divisible sum minus divisible sum. And this is the final optimized function written in Python.